Right, this is June 08 AS1 and this is question 6. A resistor of resistance 3 ohms is connected to a battery of EMF 12 volts and internal resistance 0.6 ohms is shown in figure 6.1. And so there's the circuit just a wee bit closer. You can see there's your 12 volt EMF, the internal resistance of 0.6 ohms. We haven't been given a current and we're told that there's a battery of 3 ohms, a resistor 3 ohms in the circuit. So the 3 ohm resistor is to remain in the circuit, but a variable resistor is going to be connected between points X and Y to provide a means of adjusting the effective external resistance so that the maximum power is transferred from the battery to the adapted external circuit. So this part here with the variable resistor here is going to be the external circuit. It says, why is a variable resistor connected in the manner stated? Now, it's a variable resistor put in here. Maximum power occurs whenever the resistance of the internal resistor is equal to the external resistance, but this is much bigger. So you'll get maximum power transfer if that 3 ohm resistance is reduced to 0.6. And the only way of doing that is to connect another resistor in parallel with it to reduce the overall resistance. So to write that down, to reduce the load resistance so that RL is equal to 0.6 ohms, a resistor must be connected. Or a variable resistor, I suppose I put in there, a variable resistor must be connected in parallel. And I'll just put in brackets, so maximum power transfer occurs. So if you put another resistor in series with this, that wouldn't work because it would just increase the load resistance. Then calculate the magnitude to which the variable resistor must be set to obtain the maximum power transfer for the battery. So we want to have our total resistance to be 0.6 ohms. That's the total resistance in this external bit of the circuit. If I maybe put a wee circle around that and say we want that load resistance to be 0.6 ohms because we want it to be equal to the internal resistance. And so therefore the total resistance is the total resistance for this bit is 0.6, and then we're going to add these two as if they were in a parallel circuit. And so we've got 1 over 0.6 is equal to 1 over R, which we're looking for, plus 1 over 3. So 1 over 0.6 minus 1 over a third equals 1 over R, and you can do this on your calculator. 1 over R comes out to be 4/3, or R comes out to be 3 over 4. And of course, as a decimal, that is 0.75 ohms. And so by connecting a resistor of 0.75 ohms, or variable resistor, set to that value, you will get an overall resistance here of 0.6. And we're just going to draw that in. It's set at 0.75. And remember, the total resistance in a parallel circuit is always less than the smallest one that's there. So you can see that should be coming out then at something lower than 0.75. Second part of the question, part B. A network of resistors is connected to the battery of EMF 6 volts and negligible internal resistance. The magnitude of each resistor is as shown in figure 6.2. And so you've got a 6 volt power supply, a 12 ohm and a 4 ohm resistor here, an 11, a 7 and a 9 ohm resistor here. And it just says calculate the current drawn from the battery. So that's a simple calculation. We first of all have to find the resistance of this parallel bit. And that's going to be 4 by 12 over 4 plus 12, which gives you 48 over 16. So that resistance there is going to come out then as 3 ohms. This part here, I'm going to do it as a product over the sum as well. The top line there is worth 18. I'll just write 18 beside it. So it's 18 times 9 over 18 plus 9. And that comes out to be 6 ohms. Right, so the total resistance down here, the total resistance in the whole circuit is your 3 plus your 6, which is 9 ohms. And now if we do our I is equal to V over R, and V is 6 and R is 9, you're going to get an answer of 2/3, or 0.67 amps.